And next up, we'll have Joris van den Bossche, who will tell us something about the GeoArrow library. So, Joris, please.
Yeah, thank you. So I'm Joris. I'm working at Voltron Data. We're a company building, composable, accelerated native data engine. That essentially, it's a lot of buzzwords for. It's a large data engine for large data, like petabyte scale data on GPU. But it's all on top of Apache Arrow. And so my work is working on the open source Apache Arrow project, especially the Python bindings by Arrow. I'm also involved in the geospatial community, and so have been working a bit on the intersection between those two ecosystems, and so that's where GeoArrow comes into the picture. Carl Byron, for the people that attended his talk yesterday, already explained quite some of the concept that I'm going to show here as well. He did that with some cool visualizations and nice applications, so I'm going to try to dive a bit deeper in the technical aspects. Maybe a question to start, like, who in the room feels comfortable to explain what Apache Arrow is? Not that many people. So let me, try that. So Apache Arrow is a standard. And so we're at an open source conference, like we all love open source packages, but in addition to open source, having open standards is also very important for interoperability between different packages to enable innovation. Those slides are HTML slides, so all that is possible because of standards, HTML. For this talk, it's the type of standard is a standard about how to represent data in memory, because that's what Apache Arrow is about. And to give a simple example, and Carl used it as well, like consider that you have, here on the left, you have an array. To the array, you have some numbers. The way that array is represented in memory, typically for array libraries, they are represented as a single contiguous buffer. That's different, like if you would have a Python list that doesn't use that kind of memory layout, but array libraries use this single contiguous buffer. And that makes that you can very easily share that data. If you want to share, that's the buffer protocol. You essentially just point to the start of that buffer and you say something about the data types, you know, the bit width, the shape, strides, and then you can share that data very easily. And that's like a large part of the Python scientific stack is built on top of the fact that you can just share that data between libraries. That's for a single array with a single buffer. And essentially, Apache Arrow tries to do the same, but for tabular data. Tabular data is a bit more complicated, though, because you have different columns, column names. Every column can have a different data type. There are more complex data types, not just numbers, but also variable length strings. You have nested data. We want to support missing values. And so that's where Apache Arrow tries to standardize this in-memory representation. Important concept here is that you could store this row-wise. You store every row together in memory, which is what many traditional databases do, like typical transactional databases. But for analytical use cases, it's typical to store data columnar, where you store the data of one column together. And so Apache Arrow is standardizing how to store in memory, how to represent in memory such columnar data. This is one example. I'm not going to go into the details, but assume here on the left, you have a column that is a list type. So every element in your column can be a list of some values, in this case, some integers. And so what Apache Arrow does for a nested type like a list type is define like how are we going to store this in memory. And in practice, what you see on the right is that we are going to store all the integers in one buffer. We have another buffer that stores some information about missing values. We have another buffer that stores information about how the lists are divided. Without the details here, but what Apache Arrow does is for every type, define this kind of layout. Like which buffers do I need to have in memory to represent a certain data type? So that's the core part of Apache Arrow is this specification to define that in-memory representation. Very generic, nothing language specific. On top of that, there are some additional specifications that, if you then have those buffers in memory and you want to share them, within process. That's something we will see later in the presentation. Or you want to share that data to a different process over the wire, client-server communication, for example. Then there is also a specification for a very lightweight serialization, specifically for Apache Arrow. That's a part of the project that defines the standards, the specifications. Then Apache Arrow also consists of a whole set of implementations of those specifications. So there are, in many languages, there are implementations. Specifically for Python, the main implementation is PyArrow, which are bindings to the C++ implementation. And then the number of batteries included can vary a lot. Some languages just have an implementation of the standards. Some other also include a whole set of compute tools, for example, or I/O methods to work with Apache Arrow data. So I explained what Apache Arrow is, and so the two main motivational use cases for which Apache Arrow was started is, one is we want to move data around, and we want to efficiently move data around. So, for example, in the past, many data systems, the example here is R and Python, but also database. They all have their own internal representation. If you want to move data from R to Python or from Python to Spark, you need to do a lot of copy conversions, costly serialization, while we can, if you have a standard and all those tools are Python, Spark, all those tools speak the same language for how to represent data in memory, we can do that a lot more efficiently. We can also share implementations, for example, for a Parquet reader. As long as it reads the data into Arrow memory, then any other tool that speaks Arrow can reuse that implementation. So that's one thing, is moving data efficiently. We also want to process the data efficiently, and the Arrow format is not just for moving and interchanging data. It's also meant to be an efficient format to just process your data in memory. So I already mentioned that it's columnar, which means that it's optimized for vectorization, so you can have efficient algorithms working on the data itself. So moving data efficiently, computing efficiently, that's all things that are relevant for geospatial as well. And so, the question is then, how can we leverage those new standards and tools also in the geospatial ecosystem? That's an image from Kyle's presentation. So at this idea of improving interoperability, we can also apply that to the geospatial ecosystem, where we could have on the right side, that's the vision. Certain of those lines already exist, and not all of them, but that's the vision where we want to go to. And I want to focus on one specific line here from GDAL to GeoPandas as an example to explain a bit more in detail how this works. So GDAL, I think everyone is aware, knows GDAL. It's the library that can read any kind of file format, geospatial file format. And most libraries that want to read those files use GDAL under the hood. So the way that this works in practice is, if I focus on GeoPandas for a moment, if you read a file, it's GDAL that will read the file. It's a GeoPackage file. So GDAL reads that GeoPackage file, reads that data in memory, and then GDAL exposes an API to get row by row the data. And so in GeoPandas, when we are using Fiona, we will actually get row by row through a Python object. PyOgrio already improved a bit on that by directly building up an array, but still getting the data row by row. And so getting this data row by row from GDAL, moving that data row by row to Python, that's not very efficient. And so that's where Apache Arrow can improve this data interchange. And so since a few releases of GDAL, there is a feature in GDAL to ask if you have a data set, you open a layer, you want to get that data in batch by batch using Arrow memory. And to give you a few examples of how that improves speed for getting data into GeoPandas. So these are some benchmarks reading a GeoPackage file, or well, different file formats, but the GeoPackage file is around like a gigabyte. It's 3 million polygons, the building outlines of New Zealand. And here on the graph, you see the improvement of using PyArrow instead of Fiona. So that's still reading row by row, but already doing that at a lower level on the Python side. Now, if you can let GDAL construct the data, the tabular data, and move it in batches to Arrow, to Python, instead of moving it row by row, we can improve that further quite a bit. So for example, for GeoPackage, you get a further 4 to 5 times speed up. It depends on the format, because it depends a bit whether GDAL has a specialized implementation to read directly the Arrow data from the file formats. But for example, for GeoPackage, that's the case, and you see a further very nice speed up. This is not the default in GeoPandas, so if you want to use this, want to try that out, you have to specify this use Arrow equals true keyword, but that's something you can try out. Focusing on those two bars, so leaving Fiona out of the picture, so we can zoom in on this part. So you see the speed up from using Arrow to move data from GDAL to Python. And I want to clarify that those bars, those orange bars that you see here, that's still both GDAL reading the data and moving it to Python, as well as then creating a GeoPandas geodata frame, which means that we create shapely objects under the hood. So there is a large part in this timing dedicated to creating geometries. So if you just focus on reading the data from the GeoPackage file into memory, into Arrow memory, there is a PyArrow read Arrow function. And then you can see that essentially like a gigabyte GeoPackage file with 3 million polygons, we can read it in about a second, all thanks to this improved interface with GDAL using Arrow. That's the high level, or well, the bit higher level about like using Arrow to move data from GDAL to Python. But so how does this actually work in practice? Because like GDAL constructs Arrow data, and it's not that we have to copy that data to Python then. We actually can reuse that data once it's in Arrow memory, zero copy. And the way that this works is thanks to the CData interface. And so if you think back to the beginning of my talk where I mentioned the buffer protocol, where you have an array, which is essentially a single buffer, and we can share that buffer by just pointing to the start of the buffer and giving a little bit of metadata. So we can do exactly the same for Arrow memory. It's just a little bit more complicated because we don't have a single buffer, but we have a whole set of buffers, depending on the data type. But that's essentially what the CData interface is. It defines a small struct, a C struct, with this information that you then can easily share with another implementation. And what you're essentially doing is sharing like the memory location, you share a pointer to the data. So GDAL constructs the Arrow memory and just shares with Python. This is the pointer here. Does the buffers live in memory, and you can reuse that same memory. And that's actually the already widely used. So if you have Polars or DuckDB and they share data with Pandas or PyArrow or some other libraries, that's all already using like this zero copy sharing of data using the CData interface. In practice, there is like, this is a small example of the struct. I'm not going to go into detail, but essentially what you're doing here is you're pointing to, some like pointers to buffer locations, essentially. That's how it works in like at the low level, like sharing a pointer to that struct. But so how does this work in Python? And the PyArrow has a function OpenArrow, which gives you like a generic arrow reader for a certain file. So I'm opening here, I let GDAL open the geopackage file, and what OpenArrow returns is a reader object that gives you the arrow data batch by batch. And then I can consume that data, for example, using the GeoArrow Rust library, or I can just consume that data with PyArrow or with GeoPandas from Arrow function. And they all will convert that data in Arrow format to their own internal representation, which can also be Arrow or something compatible with it. And the way that this works, because we just have like the C data interface itself is a C struct, but here we are in Python. And so what a layer on top of that is called the Arrow PyCapsule interface, is that we are going to pass this pointer to this C struct from the C data interface through Python using a capsule object, which is an object from the standard library of Python specifically meant for passing pointers around through the Python layer. In addition, it defines a few dunder methods, like the double underscore methods, that then will return those capsule objects. And that's also the way that we can recognize that another object is something that represents our data. So if you have an object, a class like a table object or a reader, and you support converting yourself into our memory, you can define an arrow, like this dunder arrow C stream methods, which returns a capsule with a pointer to the information about where the memory, where the buffers are in memory. And essentially, in the previous slide, so when PyArrow opens the file and returns a reader, that reader has this dunder arrow C stream method defined. And so any of those independent implementations, they will just, like, if they receive an object, they will check, does this object have this dunder arrow C stream defined? And if it has, they know, okay, I can call that method, I will get the capsule with information about where the data lives, and I can just zero copy, reuse that memory. So that's how it works on the Python side. Now, I've mostly been talking about Arrow, and actually talk about GeoArrow. So let's bring in a bit more the geospatial part. So Arrow itself doesn't have any geospatial specific knowledge or data types, and so GeoArrow is an effort to agree on how do we represent geospatial data in Arrow. If you go back for a moment to the example of moving data from GDAL to Python, we can use an Arrow memory, like an Arrow table, to move the data from GDAL to Python, but we still need to know on the Python side, like which column are geometries and what kind of geometries are it, or what's the coordinate reference system. And so that's what GeoArrow tries to do. So GeoArrow, in the one aspect of GeoArrow is that we define a set of extension types. So that's a concept from Apache Arrow where you can essentially annotate any built-in data type, where you can say for like more application-specific type, like this column is a GeoArrow data type. For example, this column is a GeoArrow polygon type. And you can also specify some metadata to annotate your column. For example, I had to preserve some information about the coordinate reference system. The second aspect about GeoArrow is that we still need to, the actual data in the column, like how do we store geometries in that data? And the simplest choice is to still use some kind of serialization. For example, or typically well-known binary. So at the moment, if you, in this scheme of moving data from GDAL to Python, most of the time this will use, at the moment, well-known binary in the geometry column. But yeah, we can do better given that we are moving data from one system to another. And well-known binary is again some kind of serialization. And so we want to avoid that as much as possible. And we can also define like more our native ways to store geometries in our geometry column. And that's where yeah, GeoArrow defines a set of such data types. So Arrow itself doesn't have any geometry specific knowledge, but it has a whole set of types, existing types that we can use. And if you consider like this GeoJSON representation of a polygon, what we have here, so it's a simple polygon with like an exterior and interior. And the way that GeoJSON represents this is essentially as a list of two rings, exterior ring, interior hole. And every ring, again, is a list of coordinate pairs. So what you have here is a list of two items. And while Arrow doesn't have like a specific geometry type, it does have a list type. And you can nest lists, so you can create a list of a list of lists. And so if you represent this type of data in Arrow, like if you translate this GeoJSON structure to like the native memory of Arrow, we can represent this as a list of a two-item list. And then the way that this is represented in memory is that all the coordinates, like this final XY two-item lists, that's just stored as a single array. So we have, this is an example showing one polygon, but we typically have a column with many polygons. And so all the coordinates of all your polygons are essentially stored in one array of coordinates. And then in addition, the way that Arrow works for nested lists is that you have, you keep track of offsets. So in this case, for example, we say like from coordinate pair 0 up to 5, that's my first ring. From coordinate pair 5 up to 9, that's my second ring. And then we have, additionally, because we have polygons, we say like the ring 0 up to 2, that's my first polygon, and then continuously for other polygons. And this concept translates to every possible geometry type, as long as, and that's the limitation of this format, is as long as you have a column with only polygons or only line strings. Multi-polygon, for example, will add one more level of nesting, because there a multi-polygon is a list of polygons, so then you get a list of a list of a list of a fixed size list. This is showing the fixed size list where you have essentially an interleaved array of coordinates, so xy, xy, xy in one array. There is also a version, and it depends a bit on the application, which is most useful, where you essentially store your coordinates as two separate arrays, like one array with all the x's, one array with all the y's. But that's, yeah, very briefly explained what GeoArrow, the native memory layout of GeoArrow is. And if you go back to this image of moving data, so when we're moving data, for example, from GeoPandas to like a visualization library, Kyle should have included his visualization library here on the slides, because essentially it's also using that. If you would use well-known binary, you would have to, GeoPandas would need to create a well-known binary, and then we move that data to Lonboard, and Lonboard would again have to like deserialize the well-known binary. And so there are two steps that are unnecessary here, and Arrow is all about avoiding unnecessary serialization. And so if you use this GeoArrow native formats, we can much more efficiently move data from GeoPandas to Lonboard, because Lonboard also essentially uses this GeoArrow layout directly to compute. Because it's not only, we don't only want to use it to move data around, it's also to process data. And so you already have a set of libraries that essentially use GeoArrow or GeoArrow-like memory to directly compute on. Like for the visualization example, you just need access to the coordinates and know like where a new polygon starts. And so that's much more efficiently to do that on like one array of coordinates instead of something like well-known binary that you have to parse, or GeoJSON that you have to parse. Some other examples, Data Shader is another visualization tool that also uses a very similar layout under the hood. GeoArrow Rust library, QSpatial, GPU implementations of spatial algorithms use also a very similar layout. Certain data types in DuckDB Spatial use a similar layout. And so, yeah, this is, we are, like in GeoArrow, we are convinced that also, not just for moving data around, but also for compute, it's a very efficient format. Very small example to end here, like showing two implementations of those ideas of GeoArrow, the memory format. So I have a colleague, Joris, who has implemented a GeoArrow PyArrow package. So using PyArrow and building on top of PyArrow to implement those data types. And so, for example, I can create here, starting from some well-known text, but parsing that into GeoArrow memory, create an array of 2 polygons. Then there is a completely independent library that Kyle is working on in Rust, GeoArrow Rust. It defines some algorithms that work directly on GeoArrow memory. And for example, very simple example, you want to calculate the area of every polygon. And so what we can do, because of GeoArrow memory and because of the capsule interface, that those 2 independent libraries can actually recognize each other. We can pass that array of the PyArrow array, we can pass that to the Rust function, the Python bindings of the Rust function. On the Rust side, it will see it's Arrow compatible data. I get that data, I get that data 0 copy, and I can compute, I can process that data and calculate the area in this case. So a few things that were I myself involved, or some of my GeoArrow colleagues. So GeoPandas 1.0 will have functionality to import and export to GeoArrow. I already mentioned the GeoArrow Rust library from that Kyle is working on, the GeoArrow PyArrow library that my colleague at Volten Data, Joris, is working on. Shapely also has some functionality to convert Shapely geometries to essentially the same layout, which is called to ragged array and from ragged array. And so, yeah, you can find more information on the geoarrow.org websites or the repos. And so, yeah, we're just a few people trying to think about how can we work with geometries in GeoArrow. So any feedback or involvement is always very welcome. So that was my talk. Here is a link to my GitHub or Mastodon handle if you want to contact me.
Thank you, Joris, for this deep dive into Arrow and GeoArrow. We have time, I guess, for 1 or 2 questions. Are there any questions in the audience? Oh, yeah, there's one in the back.
Thank you. Thanks, Joris. In your GeoPython example at the beginning of the presentation, there was a read file function, and you passed the to arrow or from arrow options. So, yeah, use arrow. Is there any why it's not always true? And is there advantages or inconveniences?
It's a good question, and we have been discussing it internally because it just gives most of the time it just gives another speed up. The thing is that for certain data types, it's not exactly giving the same result as the current implementation that like does it iteratively. So like I think for dates, it's giving instead of Python datetime objects, it's converts to NumPy datetime 64. Like there are a few small differences, and that's the main reason that we decided to not yet turn it on by default. But yeah, we should at some point do it.
Okay, unfortunately, we have to move forward with the next talk. So thanks, Joris, again.